All right, welcome to Chapter 1, Sampling and Data. All right, so I definitely recommend that you read Chapter 1 in your online textbook uh, in, in conjunction with this lecture. It'll help you understand things better. All right, so first, Section 1.1, Definitions of Statistics, Probability, and Key Terms in an Introductory Statistics. So there's your first definition right there, statistics. What is that, right? So that is the science of collecting, organizing, analyzing, and interpreting data in order to make decisions. All right. So a few things about definitions in this class, for my class anyway. I don't ask you to repeat or write down word for word definitions. You just need to understand and be able to apply the definitions. Okay, and we'll do some example questions throughout this lecture. All right, so the red parts you're definitely going to write down in the notes. On your set of notes, they'll be blank. So you might want to pause these videos as you write stuff down. All right, next thing we have descriptive statistics. And what's kind of cool about a lot of the terminology in this class is these words are self-descriptive. Literally, this one, descriptive statistics. Right, in this course, you'll learn how to organize and summarize data. Organizing and summarizing data is called descriptive statistics because it describes the statistics, right? Pretty cool, huh? All right, the next term we have is inferential statistics. So again, let the words help you define them. Inferential statistics, to infer something, means to make an educated guess. And that's what you're doing with this stuff, with inferential statistics. So after you've studied probability and probability distributions, we will use the formal methods for drawing conclusions from good data. The formal methods are called inferential statistics. So infer, we're going to take some data, make an inference, and make a decision. The goal of statistics is not to perform numerous calculations using the formulas, but to gain an understanding of your data. That's important, to understand the data. The calculations can be done using a calculator or computer. The understanding must come from you, right? And part of that understanding, or a big part of that understanding, is you knowing these definitions and understanding and being able to apply these definitions. If you can thoroughly grasp the basics of statistics, you can be more confident in the decisions you make in life, right? So it's kind of a common question for math students. When am I ever going to use this stuff? Well, statistics is one of the best math classes ever because you will use it every day, right? In analyzing statistics, numbers, data, where did they get the data from, that kind of stuff. All right, so this is a good class to take, not just to get your degree, but good for analyzing real-life data. Let's see, then we'll go on to probability. Probability is a mathematical tool used to study randomness. So it deals with the chance, the likelihood, of an event occurring. For example, if you toss a fair coin 4 times, the outcomes may not be 2 heads and 2 tails, right? It could be a mixture of those two. However, if you toss the same coin 4,000 times, the outcomes will be close to half heads and half tails. And that's something we'll talk about later on. All right, so statistics is based on the theory of probability. So the theory of probability began with the study of games of chance such as poker. Right, you know, people playing those kind of games, poker, etc., they're trying to make money, right? So where there's money, people want to, maybe want to try to cheat the system or figure out a more efficient way. Well, statistics and probability does that for you. Predictions take the form of probabilities. To predict the likelihood of an earthquake, of rain, or whether you will get an A in this course, we use probabilities. Doctors use probability to determine the chance of a vaccination causing the disease that the vaccination is supposed to prevent. Okay, so there is a chance of that, but it's extremely small, or that's what they hope for. Let's see, so more key terms here. Population. I know you've heard this word before, but here's a little bit more of a formal definition. So in statistics, we generally want to study a population. So you can think of a population as a collection of persons, things, or object under study. In other words, the stuff that you're analyzing. Okay? So here's a quick example. Determine the population. So we want to know the average, mean. So you'll see this word quite a bit in statistics. The word mean does not mean teacher. It means average. Okay? So the mean amount of money first-year college students spend at SCC on school supplies that do not include books. So we randomly survey 100 first-year students at the college. 3 of those students spend $150, $200, and $225 respectively. Right? So they want to know, what is the population of study here? Well, we're studying all first-year students attending SCC this term, because that's who we're questioning. That's who we took a sample from. Okay? Speaking of the word sample, to study a population, we select a sample. The idea of sampling is to select a portion or subset, a smaller piece of the larger population, and study that portion, the sample, to gain information about the population. And of course, the reason we normally do this is to save time, save money, save effort, right? I don't know how many SCC students there are, but I think there's somewhere around 12,000. It'd be very tedious, and you're probably not even going to get all 12,000 people to answer a survey about how much they spent, not including books. But if you do a proper sample, and the keyword is proper sample, then we can use a proper sample to estimate the population data. All right. All right, so here's another example here. Determine the sample. So we want to know the average mean amount of money first-year students, again, spend at SCC. So those were the 3 students. They spent $150, $200, and $225 respectively. So the sample could be all students enrolled in one section of a beginning statistics course. Right? We could go to a specific class, sample a few people, and hopefully draw some conclusions about the population from that sample. All right, next term here is a parameter. So a parameter is a number that is a property of the population. So parameter goes to population, the letters P and P. All right, so a parameter is a number that is a property of the population. So because it takes a lot of time and money to examine an entire population, sampling is a very practical technique, and that's what I was just talking about. All right, so let's determine the parameter of this example that we've been using. Let's see. So again, same example that we've been using every time here. So in this case, the parameter is the average amount of money spent, excluding books, by first-year college students at SCC this term. Okay, so parameter comes from the population. So the parameter in this case is that average amount of money spent by these students. All right, the next term you want to make sure you understand is statistic. So a statistic is a number that represents a property of the sample. So it's kind of easy to remember. Statistic, sample, SS. Parameter, population, P and P. Okay? All right. So for example, if we consider one math class to be a sample of the population of all math classes, then the average number of points earned by students in that one math class at the end of this term is an example of a statistic. Okay, so again, same example that we've been working on here. Let's find the statistic. All right, so the statistic is the average amount of money spent by these first-year students, this time in the sample, not in the population, right, in the sample, because a statistic goes with a sample, SS. Okay, moving on. So variables, right? You've heard that term numerous times in your mathematical career throughout school. Variables, letters that represent numbers that can change, right? So a variable notated by capital letters such as X and Y, is a characteristic of interest for each person or thing in a population. All right, so in this case, determine the variable again, same example that we've been working on. So in this case, the variable could be the amount of money spent excluding books by one first-year student. All right, so one particular this time. So let's say we could define the random variable, the variable x, and let x equal the amount of money spent excluding books by one first-year student attending SCC. Right, because that letter x, that variable, can change. Right, and we know that because we saw some examples right here of how those variables can change. Okay. All right. So variables may be either numerical or categorical. All right. Again, let the terms help us define them. So numerical, numbers, right? So things that we can count, things that we can measure. All right. So numerical variables take on values with equal units such as weight in pounds, time in hours. All right. Then we have categorical. You see in the word categorical, we see the word category. Right? So these are things that describe. So categorical variables place the person or thing into a category. Right? You have like cars, trucks, vans, SUVs, etc. Those are categories. They're not numerical, but they do describe the groups of data. If we let x equal the number of points earned by one math student at the end of a term, then x is a numerical value, right? Number of points, numerical value. If we let y be a person's party affiliation, then some examples of y include Republican, Democrat, Independent, etc. So that's a categorical variable, because those are categories. All right, another important term, data. We're going to use that word a ton through this class. So data are the actual values of the variable, right? So if we count how many cars each family has, then the answer could be 0, 1, 2, 3, etc. That's the data. In this case, they may be numbers or words. We just talked about that, either numerical or categorical data. The word datum is a single value. All right. So again, same example, this time determine the data. Right? In this case, we have some numerical data, which was the amounts that each student spent. All right, so on to the next section here. 1.2, data, sampling, and variation in data and sampling. So data types. So we just kind of talked about that a little, but now we're going to get a little more in depth. So data may come from a population or from a sample. So quick recap. So data that comes from a population is called a parameter. And data that comes from a sample is called a statistic. All right, so small letters like lowercase x or lowercase y generally are used to represent data values. Most data can be put into the following categories. So we have these two categories right here, qualitative and quantitative. Again, let's let the words help define them. Qual, so that's like a quality, right? So that's that categorical data again. So qualities, color, type of vehicle, that kind of stuff. Then we have quantitative, so quantities, numerical data, right? Okay, so there we go. A little bit more formal definitions here. Qualitative data. So qualitative data are the result of categorizing or describing attributes of a population, like color of a vehicle, type of a vehicle, type of calculator you have, something like that. Also, hair color, blood type, ethnic group, the type of car, the street a person lives on. That's qualitative data because it's qualities. It describes non-numerically. And there it is. Qualitative data are generally described by words or letters. All right, and then we have quantitative data. Again, the word quantity. So that's always numbers. Quantitative data are the results of counting or measuring, and this is important, you'll see why in just a minute. Counting or measuring attributes of a population. Amount of money, pulse rate, weight, number of people living in your town, the number of students who take statistics are examples of quantitative data, because we can either count or measure those things. Quantitative data may be either discrete or continuous. So here we go, two terms right here, discrete and continuous data. So quantitative data can also be broken down into discrete and continuous data. So discrete, all data that are the result of counting. So this is the big picture here. Discrete data are things we can count, usually involving whole numbers, and we'll talk about some examples in a minute. But if we count how many students are in a classroom, you're definitely not going to get 35 and a half people in the room. I mean, if we have half a person laying on the ground, that's a mess, and someone's probably going to jail. All right. So these data take on only certain numerical values, and that's what I'm talking about, mostly whole numbers. If you count the number of phone calls you receive for each day of the week, you might get values such as 0, 1, 2, 3. Because when you're counting the number of phone calls, it's either a phone call or it's not. You can't say you got half a phone call. All right. All right, next one here, continuous data. All data that are the result of measuring. Okay, so continuous data is data we can measure. That's important. These are quantitative continuous data, assuming that we can measure accurately. If you and your friends carry backpacks with books in them to school, the number of books in the backpacks are discrete because you can count the books. It's either a book or it's not. You're not going to get half a book in there. And the weight of the backpacks are continuous data, right? So weight is something we can measure. So continuous data. Okay, and again, real quick, discrete, something we can count, continuous, something we can measure. That's important. You will see those on tests and quizzes and homework. Okay. Let's see, so example. So you go to the supermarket and purchase 3 cans of soup. Let's see, 19 ounces of tomato bisque, 14.1 ounces of lentil, 19 ounces of Italian wedding, 2 packages of nuts, 4 different kinds of vegetables, 2 desserts, and 2 pounds, 32 ounces chocolate chip cookies. So there we go. Lots of stuff you bought. Name data sets that are quantitative discrete, quantitative continuous, and qualitative. So again, real quick, discrete are things we can count, usually whole numbers. Continuous are things we can measure. A lot of times those will have decimals. They don't have to, though. And remember, qualitative, the qualities. Non-numerical. Right? All right, so here's some possible solutions to this question. Let's see, the 3 cans of soup, 2 packages of nuts, 4 kinds of vegetables, and 2 desserts are quantitative discrete because you can count how many of each thing you bought. It's either a can or it's not. You can't say, again, that you have half a can or half a bag. Another possible solution here, we can talk about the weights. Right? So weight is something we can measure. So those are quantitative continuous. We also have a third option here, types of soups. Right? So types of soups, nuts, vegetables, and desserts are qualitative because they describe their qualities of the things you bought. All right, so here's another example. This would be a typical test or quiz type question for sure. Let's see, so determine the correct data type, either quantitative or qualitative. Now, if it's quantitative, let's talk about if it's continuous or discrete. Okay? All right, so letter A here, the number of pairs of shoes you own. All right, so number of pairs of shoes you own. It's definitely something you can count. And either you have a pair of shoes or you don't. You can't say you have 3/4 of a pair of shoes. That doesn't make sense. Okay, so that's quantitative. And since it's quantitative and we can count it, it's discrete. Okay, quantitative discrete. All right, B, the type of car you drive. So that's definitely non-numerical. So that's qualitative. C, the distance it is from your home to school. So distance, that's definitely numerical. So quantitative, I'm going to abbreviate here, quantitative. And it's a distance, so a distance is something we can measure. So that's continuous. So quantitative, continuous. All right, letter D, the number of classes you take per semester. Right, and when you say how many classes you took, again, you're not going to talk about, you took half a class or 3/4 of a class or something like that. You either took the class or you didn't. So that is, so number, so it's something we can count, so quantitative. And we're counting it, so that's discrete. All right. Letter E, type of calculator. So it's non-numerical, so that's qualitative. It's a quality of the calculator. The weights of wrestlers. Weight, definitely numerical, and something we can measure. So again, that's quantitative. And in this case, since we can measure it, it's continuous. All right, part G, the number of correct answers on a test. So number, again, so that's definitely quantitative. And you either get the answer right or it's not, right? So this is definitely discrete. Okay, again, that's a typical test or quiz type question. All right, moving on here. So displaying data. Tables are a good way of organizing and displaying data, but graphs can be even more helpful in understanding the data. There are no strict rules concerning which graphs to use. Two graphs that are used to display qualitative data are pie charts and bar charts. So you've seen those before, right? So let's say we have some sets of data here, right? Number of full-time, part-time students and totals and things like that. Okay, so we have some data right there. We can use that data to make a pie chart, right? And there we go. Pie charts look like pies. The slices represent the approximate percentage, the approximate amount of each category. All right. So now, if you're asked to draw a pie chart on a test or a quiz, just make sure, because it's all on computer for this class, so make sure you just follow the directions and fill in everything that they ask you to fill in. Okay. In general, we're going to stick with percentages for the slices of pie. And you can do it like they did it here with a legend, or you could just write those words in there too. Like we could write, FT for full-time and PT for part-time inside the graph, and then skip that if you want. Okay? But either way, either a legend like that or label the slices themselves. Okay? Sometimes the percentages add up to be more than 100% or even less than 100%. But that's usually due to rounding issues. Okay, in the real world, of course, in reality, you've got to get 100% of your data. So in the graph below, the percentages add to more than 100% because, and in this case, because students can be in more than one category. So if you add those up, that's why it shows 150.5%. Because you can be, let's see, for example, you could say you're a full-time student and you're under 25. So you're double counting those people. All right. All right, and then we have bar graphs. Again, let the word describe itself. Bar graph uses bars. The key here is that there's space between the bars. That's important. All right. So kind of star that, write it in there. For a bar graph, there has to be space between the bars. Okay? So whenever you label a bar chart, when you draw one and label one, make sure you label everything you can, right? In this case, we'll talk about these terms later, but this is called frequency. Okay? And at the bottom there, across the bottom, this stuff is category, right? Category of the student or something like that. So you've got to label your axes, right? In other words, label them with numbers and a term so we know what those numbers mean. All right? Same with the bottom here. Again, you're going to draw bars, and these bars have to have space between them for a bar chart. Okay? And then you just make the bars the height of the frequency or relative frequency. And there you go. That'll get you full credit on a test or quiz. All right. The particular bar graph below can be difficult to understand visually, so this one's kind of a mess. Like, you got bars going up and down and all that stuff. But the other graph is what's called, so this one down here, this is called a Pareto chart. A Pareto chart. It's just simply a bar chart, but where the bars go from largest to smallest. It just makes the data easier to read. So if someone, asks you on this graph here, who has the least amount, you kind of have to look back and forth like, okay, which bar is the shortest? Oh, the shortest, okay, that one right there. Whereas on this one, it's easy. You just look at the end. Shortest bar's on the end. Okay, so it's just another way of showing your data. All right, let's see some more stuff here. So sampling. So gathering information about an entire population often costs too much or is virtually impossible, right? Instead, we use a sample of the population, and this is the big key in statistics, right? You're trying to save money, save time, but be as accurate as possible. Statistics are very rarely 100% accurate. So instead, we use a sample of the population. A sample should have the same characteristics as the population it is representing. Most statisticians use various methods of random sampling in an attempt to achieve this goal. All right, so simple random sampling. So simple random sampling is a straightforward method for selecting a random sample. Go figure, right? So here's an example of simple random sampling. Give each member of the population a number. Of course, this would be for smaller populations. Use a random number generator to select a set of labels, right? So a set of numbers. These randomly selected labels identify the members of your sample, and that's who would win, or whatever you're trying to take a sample of. All right, so for example here, suppose Lisa wants to form a 4-person study group from her pre-calculus class, which has 31 members. So to choose a simple random sample of size 3 from the other members of her class, she could put all 30 names in a hat. Shake the hat, close her eyes, and pick out 3 names. You've seen that before. But a more technological, more fair way is for Lisa to first list the names of the members of her class together with a 2-digit number. So, label every person in the class from number 1 to 31. All right, and then use your calculator to generate random numbers. You're not going to be asked to do this on a test or quiz. You can Google that process, but it's not necessary. Okay. All right, now we have another type of sampling here, and these are important to know, these sampling methods. We next have what's called a stratified sample. Again, let's let the words help us define them. So stratified, strata, if you remember that word, like the stratosphere, it's the layer of gases in our atmosphere. The strata of the earth, the different layers of the crust of the earth and all that. So let's see, just choose a stratified sample, divide the population into groups. That's your strata, that's your layers. And then take a proportionate number from each stratum. Stratum is just plural for the strata. That's the key right there, from each. So we're going to divide our population into groups and then take a sample from each group. That's the key for a stratified sample. Again, you need to know these definitions, but not word for word. Just understand how to apply them. So here's an example. You could stratify means group your college population by department, math department, English department, art department, etc. Then choose a proportionate simple random sample from each department to get a stratified random sample. Suppose there's 5 departments and you want to choose a sample of 50. So 5 departments, you want 50 people. Choose 10 people from each department using simple random sampling. So SRS right there, that means simple random sampling. Let's see, that's one stratified. Now cluster samples are similar to stratified, and people get these confused all the time. So make sure you know these definitions well. A cluster sample. So to choose a cluster sample, divide the population into clusters, those are your groups again, and then randomly select some of the clusters. And then from those randomly selected clusters, you survey all members in the clusters you chose. Okay? So you can see where cluster and stratified sampling can get mixed up. So again, stratified, you make the groups, sample from each group. Cluster, you're going to set your groups, then you're going to randomly select some of the whole groups and then survey everyone in the randomly selected groups. So not every group that you begin with will get sampled from. Okay. All right. Next one here, systematic sample. So again, let the word help it define you. Systematic, a system. So a system is a process, right? Usually repeated process. So to choose a systematic sample, randomly select a starting point and take every nth piece of data from a listing of the population. So what they're saying is, take every 5th person or 10th person or 20th item off the production line and test it. That's a system. It's a repeated process. For example, suppose you do a phone survey. Your phone book contains 20,000 residents listing. You must choose 400 names for the sample. Number the population from 1 to 20,000, each of those phone numbers. Then use simple random sample to pick a number that represents the first name in the sample. Then choose every 50th name after that, because that'll give you, if you choose, every 50th person out of 400 names, you'll get, out of 20,000 names, you'll get your 400 names in the sample. All right. All right, another one here, convenience sampling. So just think about this one. If you're doing something convenient, you're probably being lazy about it, right? It's just a joke, but it's a way to remember this. So convenience sampling is a type of sampling that is non-random. A type of sampling that is non-random is convenience sampling. Convenience sampling involves using results that are readily available. Usually, convenience sampling is not a good idea. For example, a computer software store conducts a marketing study by interviewing potential customers who happen to be in the store, browsing through the available software. The results of convenience sampling may be very good in some cases and highly biased, which means favor certain outcomes in others. Okay? Convenience sampling, another example is, if music, people want to know, how let's say an album by, someone more current, like Post Malone or something like that, how Post Malone's music is going to do in the general population, you would not go to a retirement home and survey what they think there. That sample, it's doing something convenient, it's being lazy, and you're definitely not going to get an accurate idea of what the general population thinks of a new artist if you're asking significantly older people. Okay? So there we go. There's a good example. Okay. All right, some other sampling methods, you'll hear this terminology a lot: with replacement or without replacement. Definitely self-explanatory, right? So true random sampling is done with replacement. That is, once a member is picked, that member goes back into the population and thus may be chosen more than once. So it's like, picking a name out of a hat for to win a prize. You read the name, person gets a prize, you throw their name back into the hat, and they may get chosen again. Maybe not, but they could. However, for practical reasons, in most populations, simple random sampling is done without replacement. Surveys are typically done without replacement. That is, a member of the population may be chosen only once. You don't want them to give the same answers 2 or 5 or 10 times. That's going to throw off your data. Okay, so without replacement, when you choose an item out of the population to be surveyed or analyzed, you do not put it back to be chosen again. Most samples are taken from large populations, and the sample tends to be small in comparison to the population. Since this is the case, sampling without replacement is approximately the same as sampling with replacement for a large population. That's the key. Because the chance of picking the same individual more than once with replacement is extremely low. All right, so again, just understand these terms. You don't have to memorize the word-for-word definitions. Next thing we have sampling errors and non-sampling errors. So when you analyze data, it's important to be aware of sampling errors and non-sampling errors. The actual process of sampling causes sampling errors. It happens. For example, the sample may not be large enough to accurately represent your population. Factors not related to the sampling process cause non-sampling errors. A defective counting device can cause a non-sampling error. If you're measuring something or whatever and the measurement device is off, that's a non-sampling error. In reality, a sample will never, this is an important concept for real life and for this class, a sample will never be exactly representative of the population, so there will always be some sampling error. As a rule, the larger the sample, the smaller the sampling error. So to get more accurate data, you're going to take a bigger sample of the population you're studying. All right, so critical evaluation here. So we need to evaluate the statistical studies we read about critically and analyze them before accepting the results of the studies. If more people did this, I think we might have a group of better politicians out there in our country. You have to analyze, where's the data coming from? Is it accurate data? Was it collected properly, etc.? So common problems to be aware of include. So these you should know, again, not word for word, but understand. Let's see. So problems with samples. A sample must be representative of the population. That's extremely important. Again, the example I used before, you're not going to ask people that live in a retirement home what they think of a Post Malone song. It's just, you're not going to get accurate data. A sample that is not representative of the population is biased. There's definitely bias there. Biased samples that are not representative of the population give results that are inaccurate and not valid. All right? So we're going to look at several different biases in sampling here. All right, so one of them right here, self-selected samples. So responses only by people who chose to respond, such as call-in surveys, are often unreliable. Because usually what's going to happen, it's going to be people who are passionate either for or against the thing or whatever that are going to respond, and you're not going to get a nice, even, accurate, proper sample. Next one here, sample size issues. Samples that are too small may be unreliable. Right? If you ask 2 people out of 1 million a question and they say no, can you really say that those 2 people represent the entire population? Definitely not. Too small of a sample. Larger samples are definitely better if possible. In some situations, having small samples is unavoidable and can still be used to draw conclusions. It's just less accurate. Examples: crash testing cars or medical testing for rare conditions. You don't want to crash too many cars, otherwise there goes the company's profit margin. All right, next one here, undue influence. So collecting data or asking questions in a way that influences the response, right? Let's say, so I'm in real life, I'm a veteran of the United States Navy. I served quite a long time ago. But if I went, to take a survey around campus, let's say, and I wear my Navy veteran hat and my Navy veteran T-shirt and red, white, and blue socks and pants, waving an American flag, and if I walk up to someone and say, "Hey, do you love America or not?" Well, most people are going to say they love it regardless of how they really feel, because they don't, they feel like that I'm influencing them, or maybe I'm a crazy person, I might go off on them if they say they don't. So that's undue influence. I'd be influencing the answers to my question, so I would get inaccurate data. All right, next one here, non-response. So think of the word non-response. No response is given. So you're going out to do a survey, or someone's trying to do a survey. The most famous non-response is, you get that phone call. You're in the middle of playing some video games or studying for statistics, right? And you get a phone call, and the person on the other line says, "Hey, do you have a few minutes to answer some questions?" Right? And what do most of us do, right? We'll probably just hang up or say no, thank you, or some of us may even curse at them or something, right? But the problem is they needed some data. They were counting on you. You didn't answer. You gave no response, so their data is now going to be skewed. All right, so the collected responses may no longer be representative of the population. Often people with strong positive or negative opinions may answer surveys as well, which can affect the results. The next one here, causality. So a relationship between two variables does not mean that one causes the other to occur. They may be related, correlated, so that's a word we'll talk about in a later chapter. Correlated because of their relationship through a different variable. An example of causality here is, this is fact, okay? In certain parts of the country, as the temperature increases, crime rate drops, right? So can we say, so that's a good, can we say that one causes the other? I mean, yeah, as the temperature drops, maybe, in certain places there could be snow and whatever. So it's really the snow, not necessarily the temperature, that's causing the drop in crime, right? Another example you could say, as people drink more hot chocolate, crime goes down as well. But again, that would be not because of the hot chocolate, but because people drink hot chocolate when it's cold, and when it's cold in certain parts of the country, it snows, and it's hard to commit crimes, etc. So we're just saying those two things, it looks like they have some sort of correlation or relationship, but the relationship may not be related to those two specific things. All right, the next one here, self-funded or self-interest studies. So a study performed by a person or organization in order to support their claim. Is the study impartial? Is it fair, basically? Read the study carefully to evaluate the work. Do not automatically assume that the study is good, but do not automatically assume that it's bad either. Evaluate it on its merits and the work done. So this, an example of this would be, you're watching a commercial and they're talking about, and I'm just making this up, but let's say almonds, right? And they're saying, wow, almonds increase brain activity, they make you happier, and this, that, all these positive things, and you look at the bottom of the screen and it says, brought to you by the people who sell almonds. So that's something you got to question. Was it just to help sell almonds, or is that real data? How did they get the data? Was it collected properly, etc.? All right, the next bias here is misleading use of data. So improperly displayed graphs, incomplete data, or a lack of context. Politicians unfortunately use a lot of that misuse of data. The next term here is confounding. So this is an important term, confounding. Think of that word. It kind of sounds like the word confusing a little bit, so that's kind of a way to remember this definition. So confounding when the effects of multiple factors on a response cannot be separated. We're confused. Like let's say if there's a weight loss drug experiment going on. So did people lose weight because of the weight loss drug, or did they just figure, well, I'm taking a weight loss drug, I may as well eat better and exercise more at the same time? We're confused. It's confounding because we don't know. Did the medication help them lose weight? Did the exercise help them lose weight? Did healthy eating help them lose weight, etc.? Confounding makes it difficult or even impossible sometimes to draw valid conclusions about the effect of each factor. All right, so these are things you're going to definitely want to go through, these biases here, and just kind of know them. All right. All right, so let's look at these sampling methods. Let's do a little quiz here. So a study is done to determine the average tuition that San Jose State undergraduate students pay per semester. Each student in the following samples is asked how much tuition he or she paid for the fall semester. So we want to know what's the type of sampling in each case. So which method of sampling are we using? All right, so A sample of 100 undergraduate San Jose State students is taken by organizing the students' names by classification. So freshman, sophomore, junior, senior. In other words, we're putting them in groups, strata, right? And then selecting the same number from each group. Okay, so we put them in groups, select the same number or close to the same number in each group. That is stratified sampling. Okay. All right. Part B here. So a random number generator is used to select a student from the alphabetical listing of all undergrad students in the fall semester. Starting with that student, and here's the key, every 50th student is chosen until 75 students are included in the sample. So every 50th student, that's a repeated process, right? So that is systematic. Systematic sampling. It's a system, a repeated process. All right. Letter C. So a completely random method is used to select 75 students. Each undergrad student in the fall semester has the same probability of being chosen at any stage of the sampling process. That's the key right there. The same probability of being chosen. That is what's called a simple random sample. SRS for short. Simple random sample. All right, part D, the freshman, sophomore, junior, and senior years are numbered 1, 2, 3, and 4 respectively. A random number generator is used to pick 2 out of these groups, but all students in each of those 2 groups are sampled. All right, so again, we set the groups, randomly chose some number of groups, and then surveyed everyone in those groups. All right, so that is what's known as a cluster sample. And remember, make sure you know the difference between stratified and cluster. Part E. Say an administrative assistant is asked to stand in front of the library one Wednesday and ask the first 100 undergrad students he encounters what they paid for tuition in the fall semester. Those 100 students are the sample. So that's kind of being lazy, right? That is your convenience sample. Okay. All right, next we have variation. So another self-explanatory term here. Variation is present in any set of data. For example, 16-ounce cans of beverage may contain more or less than 16 ounces of liquid, right? You buy a soda, it says how many ounces are inside, but it's never going to be 100% exactly the same amount in every single bottle of soda. So here's an example. In one study, 16-ounce cans were measured and produced the following amount in ounces of beverage. So you can see they're all close, well, pretty close, to 16 ounces. Some of them are a little further off than others, but they're not all exactly 16 ounces. So there's some variation. Measurements of the amount of beverage in a 16-ounce can may vary because different people make the measurements, or because the exact amount, 16 ounces of liquid, was not put into the cans. Something in the manufacturing process went wrong. Manufacturers regularly run tests to determine if the amount of beverage in a 16-ounce can falls within the desired range. Right? You don't want to be selling a 16-ounce can of soda and only putting 14 or 15 ounces in. Your customers will get mad. All right, moving on here. So what section 1.3, frequency tables, and levels of measurement. So here's 4 levels of measurement, and we'll talk about these in just a second here. The way a set of data is measured is called its level of measurement. Go figure, right? Correct statistical procedures depend on a researcher being familiar with the levels of measurement. So not every statistical operation can be used with every set of data. Data can be classified into 4 levels of measurement, and they go from lowest to highest here: nominal, ordinal, interval, and ratio. And we'll define those right here. All right, so nominal. Again, let the word define it. Nominal is kind of the word name, right? So nominal scale, data that is measured using the nominal scale, is qualitative, categorical, right? Qualities, categories. So categories, colors, names, labels, and favorite foods, along with yes or no responses, are examples of nominal data. Nominal scale data are not ordered because there's no numerical value to it. For example, trying to order people according to their favorite food does not make any sense. Putting veggie pizza first and vegan sushi second, it doesn't mean anything. There's no numerical order to those terms. All right, the next level of measurement is the ordinal scale. So think of that word ordinal. Order. All right? So data that is measured using an ordinal scale is similar to the nominal scale, but there's a big difference. The ordinal scale can be ordered, right? So an example of ordinal scale data is the list of military ranks in the United States. The military ranks can be ranked from bottom to top, but we can't measure differences between the data. So in other words, they're words, so they're nominal, but they have a natural order to them. Okay? But you can't say, one is, this 3 times better than the other or something like that. Right? So that's what they're saying. The differences between the data don't make any sense. So again, when they're words, but they have a natural order to them, then it's the ordinal scale. All right, next one, the interval scale. So data that is measured using the interval scale is similar to the ordinal level data because it has a definite ordering, but there's a difference between the data. Like temperature, right? If we have 40 degrees, that you could look at that as 100 degrees minus 60 degrees. There's a countable difference between different numbers here. The differences make sense. But in this case, 0 degrees does not make sense because in this case, in the interval scale, 0 does not mean the absence of heat, right? Or in this case, heat. So interval scale, the number 0 does not mean the absence of the item. Okay? So 0 degrees does not mean 0 heat that exists. If you take some physics classes and all that, it's extremely lower than that when the absence of heat occurs. Okay? All right. Next one, and the last one for these, the ratio scale. So data that is measured using the ratio scale takes care of the ratio problem and gives you the most information. Ratio scale data is like interval scale data, but it has a 0 point, and ratios can be calculated, right? So 0, like if you get 0 points on the exam, there's the absence of points. If you have $0 in your bank account, you have no money. So 0 makes sense. Okay. All right. So go over those. You'll see those definitely in the homework. And here's just a quick little table to give you some ways to remember these different levels of measurement. All right, moving on here. Frequency and frequency tables. So frequency, how frequent something occurs. So things we can count, right? So here's a quick example. 20 students were asked how many hours they worked per day. Their responses in hours are here. So there's a big list of data. So this table lists the different data values in ascending order and their frequencies. So in other words, you're going to go through this list and find all the different numbers that are in there. So there's 2s, 3s, 4s, 5s, 6s, and 7s, again representing the hours these students work. So what we're going to do for frequency is we're going to go through the list and count how many 2s there are. Right? So let's see, there's a 2, there's a 2, there's a 2, right? So we have a frequency of 3 2s. The number 2 comes up in this data set 3 times. And then we'd go through and count how many 3s are in it, and you'll see there's 5 3s, 3 4s, 6 5s, etc. Okay, so again, frequency, how frequent, how often something occurs. All right, another term here, relative frequency. So relative, in relation to the whole group. All right, so relative frequency is the ratio, fraction, or proportion of the number of times the value of the data occurs in the set of all outcomes to the total number of outcomes. All right, so in other words, what you're going to end up doing to find relative frequency, you're going to add up all your frequencies, not the data values, the frequencies in your data set. And to get the relative frequency, we can see right here, right? We take the frequency and divide by the total of all the frequencies, in this case, 20. And we can get a fraction, a decimal, or even a percent if we want. Okay, so again, relative frequency in relation to the whole group. Right, and same thing up here. So there's 5 3s out of 20 total values, etc. Okay. All right, moving on. Still going on the same process here, we have cumulative relative frequency. So cumulative, it's kind of like the word accumulate, right? So cumulative data or cumulative relative frequency, we're going to keep adding the frequency, the relative frequencies up. So here's the process. So we would already have the frequencies done and the relative frequencies done. Now to do cumulative relative frequency, we're going to always include the previous set. So the first relative frequency we just transfer over to cumulative, 15% or 0.15. Then what we're going to do is we're going to take this value, add it to the next relative frequency, and that goes here. And we're just going to keep repeating this process. We take this cumulative frequency, add it to the next relative frequency, and we get this. And if you keep doing that, of course, in the end, you're always going to end up with 1, right, or 100%. Okay, because 100% of your data has been accumulated. It's cumulative. So by the end, you've accumulated 100% of everything. All right, that's an important process to know as well. Okay. All right, let's see here. Let's see, just the last little bit here. Section 1.4, experimental design and ethics. When you're collecting data, ethics always apply. Well, ethics always should apply. Taking politicians, large companies trying to make money off people and things and all that. Data can be twisted and turned and all that to make their product look better than it really is. All right, so here's an experiment. Does aspirin reduce the risk of heart attacks? Is one brand of fertilizer more effective at growing the roses than another? Is cell phone usage as dangerous to a driver as the influence of alcohol? Questions like these are answered using randomized experiments. We will look at important aspects of experimental design. Proper study design ensures the production of reliable, accurate data. Okay? The purpose of an experiment is to investigate the relationship between two variables. So here's some more terms you want to make sure you know. So this is talking about experiments. When one variable causes change in another, we call the first variable the explanatory variable. Think of the word again. Explanatory variable. It explains what happened to the other variable, right? Like if you run 5 miles a day, that would explain the outcome of the experiment, why you lost weight, right? Okay, so the affected variable is called the response variable. The explanatory variable explains the response to the experiment. So the response variable is the thing you're studying at the end of the experiment. Okay. In a randomized experiment, the researcher manipulates values of the explanatory variable and measures the resulting changes in the response variable. So, you would have one group of people maybe run 1 mile a day, another group runs 5 miles a day, another group runs 10 miles a day. Okay, so those different amounts that they're running are called the treatments. All right, so you're going to check out these treatments, different treatments, to see if they can explain the response variable, the outcome of the experiment. All right. And one last term here, experimental unit. It's just the object or individual to be measured. Okay, the person or the thing or whatever you're studying in the experiment. Those are the experimental units. All right, so here's an example. This is a typical test or quiz type question. So researchers want to investigate whether taking aspirin regularly reduces the risk of heart attack. So 400 men between the ages of 50 and 84 were recruited as participants. The men are divided randomly into two groups. One group takes aspirin. The other group will take a placebo. So a placebo is what's known as a sugar pill, a fake pill. But it looks like the same as the medication the other group is getting, because you don't want your groups knowing whether they're getting the aspirin or not, or the drug or not, or whatever thing you're giving to your experimental groups, because that could mess up your study. Let's see, so each man takes one pill each day for 3 years, but he does not know whether he's taking aspirin or the fake pill, the placebo. At the end of the study, researchers count the number of men in each group who have had heart attacks. All right, so this would be, again, a typical test or quiz type question. So let's identify the different values for this study. All right, so the population. What is the population here? The population is the men. The population we're studying is the men aged 50 to 84, right? Told you that right in there. Okay. The sample, because there's God knows how many tens of millions, hundreds of millions, or probably tens of millions men aged 50 to 84. So the sample, though, is the 400 men who participated in this particular study. It's a smaller group of the population. Part C, the experimental units. Again, those experimental units, in this case, are the individual men in the study, the people you're doing the experiment on. All right, then the explanatory variable is the oral medication. Whether they got the actual aspirin or the placebo would explain, right, the response. In this case, the response is, did they have a heart attack or not? Okay. And the last part, the treatments. What were the different things that were done to the different groups? Well, one group got aspirin and one group got a placebo. So in this case, 2 treatments. All right, so again, typical test or quiz type question here. Make sure you understand these this terminology, and can pick it out of the paragraph there. Okay. All right, here, I think this is the end. All right, there we go. Ethics, right? Again, ethics are important on everything in life, really, but especially when collecting and displaying data. So here we go. Ethics. The U.S. Department of Health and Human Services oversees federal regulations of research studies with the aim of protecting the people, the participants. When a university or other research institution engages in research, it must ensure the safety of all human subjects. For this reason, research institutions establish oversight committees, so people that look over this and say what's ethical, safe, and all that, known as institutional review boards. All planned studies must be approved in advance by the IRB. Key protections that are mandated by law include the following. So these are important. Risk to participants must be minimized and reasonable with respect to projected benefits. You don't want to do something that's going to kill a bunch of people just to see if if a weight loss drug works or not. Participants must give informed consent. In other words, you have to tell them all the risks and possible outcomes, so they know. This means that the risks of participation must be clearly explained to the subjects of the study. Subjects must consent in writing, and researchers are required to keep documentation of their consent. It helps keep people safe and all that, but also prevents or minimizes lawsuits. And the last one here, data collected from individuals must be guarded carefully to protect their privacy. That one's kind of self-explanatory. All right, so that's the first chapter of statistics for this semester. Thank